Good morning, everybody. Thank you for your attention. I am Millán García, and I am a PhD student in microstress map project. I'm going to report on the results of the recent study is carried out by our group. It is called Estimation of the Grain Level Residual Stress in a Quenched Cylindrical Sample of Aluminium Alloy AA5083 using genetic programming. I will begin by filling you in a background of the project, the recent aims, and our proposal. At follow, I will explain the methodology used, the samples, the techniques, and the information extracted from each one. After, I will describe how we can combine this information using genetic programming for obtaining the results. And finally, I will go to summarize in more depth the implication of the latest findings. This project studied the residual stress that originated during the manufacturing processes of the metallic components. Its study is important to avoid catastrophic accidents because these stress fields are retained inside the materials after the treatment. We can find two types of residual stress, microscopic and microscopic stress. These first ones are related to the geometry and the features of the piece. However, microscopic stress depends on the microstructure and the mechanical behavior of the grains. It's important to know each grains can present a different behavior according to its orientation. Nowadays, the determination of the microresidual stress remains to be a pending task. Nonetheless, we present an approach using genetic programming to obtain the microresidual stress in grains of a quenched cylindrical sample. For this work, we are focused on an aluminium alloy named AA5083. This alloy is composed of a matrix of aluminium and other elements, fundamentally magnesium. We prepare a cylindrical aluminium sample from an extruded bar. This sample is heated at 530 degrees and is quenched in water. This treatment generates residual stress inside the sample. In a second step, we extracted curves from the center and at 6 and 12 millimeters along the diameter of the cylindrical sample. After, we measured the surface in the axial direction by electron backscattering diffraction. This technique offers us a map of grains and information on the microstructure and the grain's orientation. It is represented with different colors and colored with Miller indexes. It can also apport a list of grains and their features. We commonly measure the stress using neutron diffraction. The neutron beam passes across the sample and collision with the atoms of aluminium. The beam diffracted affords us the value of the lattice spacing between planes of atoms which have the same orientation. This parameter is important to calculate the stress. Besides, we can obtain a diffractogram with 4 peaks according to the principal orientation of the grains: 111, 200, 220, and 311. The grains which generate the peaks are the same that the grains in the list obtained by electron backscattering diffraction. So we found this link between the two techniques. Consequently, it was possible to predict the lattice spacing corresponding to one orientation using a genetic programming expression depending on the variables in the electron backscattering diffraction. We choose the 111 peak profile. This expression allows obtaining the stress of each grain. We introduce the following parameters and the algorithm in the heuristic lab software. The steps in the analysis are shown in the script. "30 executions were made. The best solution was chosen considering the minimal error between the target and the predicted peak. An expression from the lattice spacing is extracted from the predicted peak, and the variables are the four microstructure factors: area, aspect ratio, number of neighbors, and slope. The following results are obtained using the localization of the grains in the electron backscattering diffraction map. We can identify the ED grain due to we have the information about its mass center, the X and the E values. In addition, we can calculate the microstress of each grains using the best expression of the lattice spacing obtained by genetic programming. An interesting finding is extracted from these results. Low stress in 111 large grains appears with soft neighbors, and high stress in 111 small ones with hard neighbors. We are analyzing this hypothesis because it's very important in our study. So finally, let me sum up our main points. This is the first time that micro-residual stress are numerically estimated at the grain level to the best of our knowledge. This cannot be solved directly using a usual supervised learning approach and requires a custom GP fitness function to link microstructural parameters of the grains to the peak profile occurred by neutron diffraction. The low error values between the predicted and the target peak profile demonstrated the validity and the quality of the method. However, the identified expression is only valid for one direction. Consequently, as a next step, the combination of the peak profile for all orientation as well as the microstructural data corresponding to the other position along the diameter of the sample should be used to identify a more general model for micro-residual stress of the grains. We hypothesize that the same GP approach can be generalized easily for this task. The result of the micro-residual stress will be compared to the microstructural features in the later study. Apparently, GP indicates that number of and the type of the grains neighbors and the size of the most important factors influence in the micro-residual stress values in 111 grains. Future work solving necessarily include a complete view of all of the orientations and other materials. So that is all. Thank you very much for your attention. Of course, you can write me at the following email if you have any questions. Have a nice experience in the rest of the conference. Bye.